In our previous lesson, we learned how to write a number in scientific notation. Now that we understand what scientific notation is, we can begin performing operations with these numbers just as scientists have to in their research. We'll begin with multiplication and division and then look at examples involving addition and subtraction. In our first example, we're told that the Confederation Bridge connects New Brunswick to Prince Edward Island. The main part of the bridge rests on piers that form 43 segments. What is the approximate length of the main part of the bridge? Express your answer in scientific notation and in standard form. Okay, and by looking at the picture that we have here, the length of just one segment is 8 and 2 tenths times 10 squared feet. Okay, so that's just one segment, and we are told that there are 43 segments. So what we're going to have to do is take the length of one of the segments, which is 8 and 2 tenths times 10 squared feet, and multiply that by the 43 segments. Notice here that I've got a number written in scientific notation and I've got a number written in standard form. Okay, the purpose of this lesson is to understand how the operations work with scientific notation. So I'm going to rewrite 43 in scientific notation. So let's keep 8 and 2 tenths times 10 squared. And now we'll multiply that by, well, 43, the decimal point is right there. Remember that we have to create a number that's between 1 and 10. So I'm going to have to move the decimal point one time to the left, which would be 4 and 3 tenths. And now when I have a power of 10 that I multiply it by, it's going to be times 10 to the first power. Okay, I moved that decimal point one place to the right, which means that I'm going to have a positive exponent there on my power of 10. So now I have 8 and 2 tenths times 10 squared times 4 and 3 tenths times 10 to the first. And remember that all of this is multiplication. Multiplication is a commutative operation. So what I'm going to do is get my constants multiplied together, 8 and 2 tenths times 4 and 3 tenths, times now my powers of 10, 10 squared times 10 to the first power. If I use my calculator, I'm going to multiply the constants together. I have 8 and 2 tenths times 4 and 3 tenths, and that equals 35 and 26 hundredths, times 10 to what power? Well, if the bases are the same and we're multiplying, all we need to do is add the exponents. So that's going to give us 10 to the third power. So our answer now is 35 and 26 hundredths times 10 to the third power. But this number is not in scientific notation because 35 and 26 hundredths isn't between 1 and 10. So what I'm going to have to do is move the decimal point one place to the left, which is going to create 3 and 526 thousandths times 10 to the, well, it's not going to be to the third power anymore. Since I moved it to the left one time, the exponent is going to increase by 1, which is going to make it 10 to the fourth. 3 and 526 thousandths times 10 to the fourth feet is the distance of the main length of the bridge in scientific notation form. In standard form, this is going to be equal to, well, 10 to the fourth. I'm going to multiply this number by 10 to the fourth. So I'm going to move this decimal point to the right 4 times. 1, 2, 3 times. A fourth time, I'm going to have to add a 0. 35,260 feet is the length of the main part of the bridge. So here we have our answer written in scientific notation and in standard form. When you multiply two numbers in scientific notation, you can regroup it with the commutative property so that you multiply your constants together and you multiply your powers of 10 together. Let's do more practice multiplying numbers written in scientific notation. In our first practice problem, we have 3 times 10 to the third power multiplied by 5 times 10 to the seventh power. Just like I did earlier, I'm going to regroup this so that I have my constants together. 3 times 5 times my powers of 10. 10 to the third times 10 to the seventh power. 3 times 5 makes 15. times 10 cubed times 10 to the 7th. Again, if you're multiplying numbers with the same base, keep the base of 10, add the exponents, we would get 10 to the 10th power. So we have 15 times 10 to the 10th power. But again, this first number needs to be written between 1 and 10, so this is not in scientific notation yet. There's the decimal point. We would have to move it one time to the left to make the number 1 and 5/10. And since we moved the decimal point to the left once, the exponent is going to increase by 1 times 10 to the 11th power. 1.5 times 10 to the 11th power is the product. In letter B, we have 2 and 6/10 times 10 to the 7th times 4 and 1/10 times 10 to the negative 3rd. Regroup it first. Get your constants together, 2 and 6/10 times 4 and 1/10. Multiply the powers of 10 together, 10 to the 7th times 10 to the negative 3rd. And now let's multiply. 2 and 6/10 multiplied by 4 and 1/10 gives us 10 and 66/100 times our power of 10. Add the exponents. 7 plus negative 3 is 4. So we have 10 and 66/100 times 10 to the 4th power. But again, our first number is not between 1 and 10. So we're going to take that decimal point and move it one time to the left. That makes our number 1 and 66 thousandths times 10 to what power? Well, once again, if we move the decimal point to the left, it's going to increase. We moved it once to the left, so it's going to increase by 1, 10 to the 5th power. 1 and 66 thousandths times 10 to the 5th power. In our next example, we're told that a space probe travels about 1 and 5/10 times 10 to the 6 kilometers per day to its destination 21 million kilometers away. How many days will it take the space probe to reach its destination? Okay, so we have to take its entire distance of 21 million kilometers and divide it by the distance that it travels in one day in order to figure out how many days it's going to take. So the total distance was 21 million, which was 21 with 6 zeros after it, 21 million. And we're going to divide that by the distance that it takes to travel in just one day. And that's going to be 1 and 5/10 times 10 to the 6th kilometers that it can travel in one day. Well, notice here again, I've got a number in standard form and a number in scientific notation. And we're going to change the number in standard form into its scientific notation. So let's keep the denominator, 1.5 times 10 to the 6th power. And let's change the numerator. I need to change this so that I have a number between 1 and 10. So I'm going to move the decimal 1, 2, 3, 4, 5, 6, 7 times. That's going to create the number 2 and 1/10. And then I'm going to multiply that by 10 to the 7th power. Now that both numbers are written in scientific notation, I'm going to go ahead and do the division. Much like with the multiplication, I'm going to group this where I divide the constants first and then divide the powers of 10. So let's just focus on the constants for right now. 2 and 1/10 divided by 1.5. 2 and 1/10 divided by 1.5 is equal to 1 and 4/10. So I'm going to have 1 and 4/10 times, and now I'll focus on my powers of 10. If you're dividing with the same base, you keep the base, so 10, and then you subtract the exponents. 7 minus 6 equals 1, so this is going to be 10 to the 1st power, and the units are days. It's going to take 1 and 4/10 times 10 to the 1st days for the probe to reach its destination. Well, what is that in its standard form? Okay, well, I'm going to multiply by 10 to the 1st power, so I'm going to move that decimal point one place to the right, which means that it's going to take 14 days for the probe to reach its destination. Okay, so again, to summarize, when we're dividing numbers in scientific notation, divide the constants together and then divide the powers of 10 together. Here we get 1 and 4/10 times 10 to the 1st days, which is the same as 14 days for the probe to reach its destination. Let's do more practice dividing numbers written in scientific notation. Calculate each quotient and write your answer in scientific notation. So notice that both numbers are already written in scientific notation. That's good. We have 4 and 8 hundredths times 10 to the negative sixth power divided by 3 and 4 tenths times 10 squared. I'm going to group this so that I divide my constants first, and then I divide my powers of 10. Let's go ahead and use our calculator to do the division of the constants. 4 and 8 hundredths, divided by 3 and 4 tenths gives us the decimal 1 and 2 tenths. 1 and 2 tenths times, now I need my power of 10. 10 to the blank power. Well, again, if we're dividing numbers with the same base, we keep the base and we subtract the exponents. Negative 6 minus 2 is negative 8. So we would end up with an exponent of negative 8. So the quotient is 1 and 2 tenths times 10 to the negative 8. Right? This is already written in scientific notation. My first number is between 1 and 10 multiplied by a power of 10. In letter B, again, both numbers are already written in scientific notation. 2 and 765 thousandths times 10 to the 21st power divided by 7 and 9 tenths times 10 to the 28th power. Let's first divide the constants. 2 and 765 thousandths divided by 7 and 9 tenths, and we get the decimal 35 hundredths. 35 hundredths times 10 to what power? Well, again, we need to subtract the exponents. 21 minus 28 is negative 7. So we get 35 hundredths times 10 to the negative 7th power. This number, however, is not written in scientific notation because my initial number here at the beginning is not between 1 and 10. So I'm going to take that decimal point and move it one place to the right. Move that one place to the right, which is going to create the number 3 and 5 tenths times 10 to what power? Well, if you move the decimal point to the right once, this exponent is going to go down by 1. Okay, so if it was at negative 7 and it decreases by 1, now it's going to be negative 8 for the exponent. 3 and 5 tenths times 10 to the negative 8th power is the quotient. So when we multiply or divide with scientific notation, the process is pretty straightforward. I'm either going to multiply or divide my constants with each other, and then I'm going to multiply or divide with my powers of 10. And then I'm just going to make sure that my decimal number at the beginning is a number that's between 1 and 10 so that my answer is written in scientific notation. With addition and subtraction, okay, we have to remember that place value matters. Since scientific notation makes every number a single digit followed by a decimal and a power of 10, the place value gets hidden. This means that we can only add or subtract scientific notation numbers if they have the same power of 10, because the power of 10 controls the place value. If they don't have the same power of 10, we will have to rewrite one of the numbers in such a way that the powers of 10 are equal. Okay, so again, we can only add or subtract scientific notation numbers if they have the same power of 10. In example 3, we're told that the mass of Earth and the mass of Moon are shown below. The Moon is 7 and 35 hundredths times 10 to the 22nd kilograms. Earth's mass is 5 and 97 hundredths times 10 to the 24th kilograms. These are approximate masses. How much greater is the mass of Earth than that of the Moon? Okay, so the Earth's mass, how much bigger is it than the mass of the Moon? So we're going to do the Earth minus the Moon to figure out how much larger the Earth's mass is compared to that of the Moon. So let's start with the Earth. It has a mass of about 5 and 97 hundredths times 10 to the 24th kilograms. And we're going to subtract off the Moon, which is 7 and 35 hundredths times 10 to the 22nd kilograms. Notice here that the powers of 10 are different. We said earlier that we can only add and subtract numbers written in scientific notation if they have the same power of 10. Since they don't have the same power of 10, I'm going to have to rewrite one of the numbers. Now, in my experience, I've always found it to be easier to rewrite the number that has the smaller exponent so that it matches the number with the larger exponent. So I'm going to keep the mass of the Earth at 5 and 97 hundredths times 10 to the 24th. And I'm going to subtract. Well, I have to rewrite this number again so that it has the same power of 10. So it's going to be something times 10 to the 24th power. The question is, what's that something? Well, it was 10 to the 22nd power, and now we've increased it to 10 to the 24th power. The exponent grew by 2, which means I'm going to have to take this decimal and move it to the left 2 times. Moving it to the left 2 times, all right, that's going to make the exponent larger. So this is going to become 0 and 735 10,000ths times 10 to the 24th power. Now that the powers of 10 are the same, all I'm going to do is subtract the constants. 5 and 97 hundredths minus 735 10,000ths. That's going to be my decimal value times 10 to the 24th power. I'm going to keep that power of 10 the same. They're both powers of 10, so I factored out the power of 10, and I'm just going to subtract the constants. So let's punch this in. 5 and 97 hundredths minus 735 10,000ths, and we get 5 and 8,965 10,000ths times 10 to the 24th, and the masses were measured in kilograms. Okay, so the Earth's mass is 5 and 8,965 10,000ths times 10 to the 24th kilograms, larger than the mass of the moon. In example 4, it says that the planet Venus is on average 2 and 5/10 times 10 to the 7th kilometers from Earth. Mars is on average 2 and 25 hundredths times 10 to the 8th kilometers from Earth. What is the average distance from Venus to Mars? Okay, so this first measurement goes from Venus to Earth. The second measurement goes from Earth to Mars. We want to go from Venus to Mars. So I'm going to have to take these two and add them together. So I'm going to have 2 and 5/10 times 10 to the 7th plus 2 and 25 hundredths times 10 to the 8th power. Once again, notice that the powers of 10 are different from each other. I have 10 to the 7th, I have 10 to the 8th. I can't add them unless the powers of 10 are the same. So I'm going to change the smaller power of 10 into the larger power of 10. So here I'm going to have something times 10 to the 8th plus 2 and 25 hundredths times 10 to the 8th. I'm going to keep that one the same. Well, I had 10 to the 7th power. I've increased it by 1, the exponent, to get to 10 to the 8th power, which means I moved the decimal point to the left 1 time. So now that makes my number 25 hundredths times 10 to the 8th power. Now that I have it written where they have the same power of 10, I'm just going to regroup the constants together. It's going to be 25 hundredths plus 2 and 25 hundredths, and then whatever answer that is, times 10 to the 8th power. If I add 25 hundredths with 2 and 25 hundredths, that gives me 2 and 5/10 times 10 to the 8th power. This number is already between 1 and 10. It's multiplied by a power of 10, so this is our answer in scientific notation. The average distance from Venus to Mars is about 2.5 times 10 to the 8th kilometers. To end the lesson, we'll do a little more practice with adding and subtracting numbers in scientific notation. Let's start with an addition problem. 3 and 7/10 times 10 to the 6th power plus 4 and 3/10 times 10 to the 5th power. Okay, different powers of 10, so I'm going to have to change one of them. Again, I like to change the smaller exponent into the larger exponent, so I'm going to keep 3 and 7/10 times 10 to the 6th. And I'm going to add to that something times 10 to the 6th power. I've increased the exponent by 1 from a 5 to a 6, which means I'm going to take this decimal and move it 1 time to the left. So this is going to become 43 hundredths times 10 to the 6th power. Now that they have the same power of 10, I'm going to add the constants, 3 and 7 tenths plus 43 hundredths, and then the answer to that will be multiplied by 10 to the 6th power. If we add 3 and 7 tenths with 43 hundredths, we get 4 and 13 hundredths. 4 and 13 hundredths times 10 to the 6th power. My first number is a number between 1 and 10, and it's multiplied by a power of 10. So there's our sum written in scientific notation. In letter B, 6 and 4 tenths times 10 to the 4th minus 5 and 9 tenths times 10 to the negative 2nd. Different powers of 10, so I can't do the subtraction yet. I'm going to change the smaller power of 10 into the larger power of 10. So I'm going to keep 6 and 4 tenths times 10 to the 4th. And then I'm going to subtract off something times 10 to the 4th power. My exponent has increased from a -2 up to a 4. That's a total of 6, okay? 4 minus -2 equals 6. So this exponent has gone up 6 times, which means I need to take this decimal and move it to the left 6 times. So I'm going to end up with the decimal 0 and 0.0000059. Okay, so that's 0 decimal, 5 more zeros, and then a 5.9. Now that the powers of 10 are the same, I'm going to subtract the constants. 6 and 4 tenths minus 0 and 0.0000059. That answer times 10 to the 4th power will be the difference. And let's go ahead and punch this in. 6 and 4 tenths minus 0.0000059. Punch those in carefully. And we get that ugly decimal right there. 6 and 3.9999941 times 10 to the 4th power. Okay, so again, our first number is a number that's between 1 and 10. We're multiplying by a power of 10. So this is going to be our difference written in scientific notation.